All right, let's dive into a really fascinating thought experiment. It's one of those questions that sounds like pure science fiction, but it's actually grounded in some very real, very cool physics. And it all starts with a simple, kind of wild idea.
And there it is, the big question. I mean, it sounds completely impossible, right? But to figure out if it's true, we've got to start by understanding why it's so unthinkable right here on our home turf. So let's set the scene here, on Earth. When you fire a bullet, its journey is, well, it's dramatic, but it's also incredibly short. And that's because it's immediately thrown into a fight against two really powerful forces. You see, the second that bullet leaves the barrel, air resistance slams on the brakes, killing its forward speed. At the very same time, gravity starts its work, pulling that bullet straight down toward the center of the Earth. Those two forces basically seal its fate from the get-go. So what does that actually mean? Well, if you fire a typical rifle from, say, shoulder height, that bullet is only going to travel about half a kilometer before gravity wins the fight. The whole trip takes just over half a second before it's in the dirt. Not exactly enough time to circle the globe. But what if we could make it go a lot faster? Well, this brings us to an absolutely brilliant thought experiment from way back in the 17th century from a guy you might have heard of, Isaac Newton. He imagined putting a giant cannon on top of a mountain and asked, what would happen if we could fire a cannonball with an insane amount of power? And this idea gets right to the heart of what an orbit really is. See, we think of it as floating, but it's not. It's actually a constant state of falling. You're just moving forward so incredibly fast that as you fall toward the planet, you constantly miss it. Newton figured that if you fire the cannonball with a little bit of power, it just arcs and hits the ground. No surprise there. More power, it goes further before it crashes. But if you could give it a huge amount of power, you'd hit this magic sweet spot. The cannonball is still falling, but the Earth is curving away beneath it at the exact same rate. It's now falling forever, without ever landing. It's in orbit. And this wasn't just some fantasy. This is literally how our modern world works. The International Space Station, all those satellites beaming down GPS signals, they are all just falling. They're just missing the Earth at thousands of miles per hour. Okay, so if going fast enough puts you in a perpetual fall around the Earth, what happens if you go even faster? I mean, is there a speed where you just stop falling altogether and break free? Oh, you bet there is. For Earth, that magic number is a mind-boggling 11.2 kilometers per second. That's over 25,000 miles per hour. This isn't just orbiting anymore. This is escape velocity. You know, every planet, every star has its own escape velocity, and it all comes down to mass. The more massive something is, the stronger its gravity and the faster you have to go to break away. If a rocket leaving Earth doesn't hit the speed, gravity will always win and pull it right back down. All right, so we've got our physics toolkit ready. We understand air resistance, gravity, orbit, and escape velocity. Now let's take all that knowledge and go somewhere where the rules of the game are completely different, the moon. This right here is the biggest game changer. The moon's gravity is just a fraction of Earth's, only about 1/6 as strong. And even better, there's no atmosphere, which means absolutely zero air resistance. So those two forces that stopped our bullet dead on Earth, one is completely gone, and the other is super weak. So, how fast would a bullet need to go to get into a stable orbit around the moon? The answer is just 1.6 kilometers per second. Now, that's still ridiculously fast, but it's actually a speed that some experimental railguns and high-powered rifles are getting close to achieving. So imagine it. With nothing to slow it down and only a tiny bit of gravity gently tugging on it, a bullet fired at this speed doesn't just arc back down to the lunar surface. Nope, it behaves just like Newton's cannonball. It starts falling and missing. It just keeps on going, falling toward the moon, but never hitting it, entering this perfect, stable orbit just above the ground. But think about it. If it completes a full orbit, where does it eventually end up? That's right, it would circle the entire moon and come right back to the exact spot where it was fired from. So, to answer our question, yes. If you had the right kind of weapon and aimed perfectly flat, you could theoretically shoot yourself in the back on the moon. It would take the bullet about an hour and a half to make the trip, but it would get there. Wild. Of course, just like Earth, the moon has an escape velocity too. It's just a lot lower. You only need to hit 2.38 kilometers per second to break free from the moon's gravity for good. And that brings us to our last, kind of mind-blowing scenario. What if you fired that bullet even faster than that? What if you actually beat the moon's escape velocity? Where on Earth or off Earth does it go then?
Well, its journey would be just incredible. First, it would break free from the moon. Then, it would be going fast enough to escape the Earth's pull. Eventually, it would even be going fast enough to escape the gravity of the sun itself. It would become a tiny interstellar traveler just drifting out into the vast, empty space between the stars forever. And this table really just puts it all into perspective. Look at those numbers. The speed you need to escape the moon is just 2.38 kilometers per second. But for Earth, it's a whopping 11.2. It's nearly 5 times harder to leave our planet than it is to leave the moon. It really is all a game of mass and gravity. In the end, something as simple as firing a gun can have these wildly different results depending on where you are in the universe. It really makes you wonder, doesn't it? What other basic things that we take for granted would have unbelievable consequences on a planet with a totally different set of rules? Something to think about. Thanks for tuning in.